You just gotta keep calm with it. All right, let's go ahead and get started. I'm going to get the sign-in sheet passed around. So today what we're going to do is actually start talking a little bit about concrete. I know that yes. So last time what we had done, there's one apiece. Last time, and really for the last week, what we had done was really try and cover some of the material that's just common to structural engineering in general, things like what your responsibilities are as an engineer, what your, how do we calculate structural loads, what design philosophies do we use, etc. Now it's time to actually start talking about concrete, start talking about steel and how these two materials work together in the world of reinforced concrete design. Now, excuse me, before I get into this, one thing I'll point out, I am not in any way, shape, or form going to delve super deep into material behavior, okay? Whether or not you've had it yet or not, you will take a course CE 321 Civil Engineering Materials. And for instance, when you take that class, how many of you have already had it? Okay, so when you're in that class, Professor Huffman, I know, does a damn good job teaching you all how to do a concrete mix design, right? Well, I'm not teaching you how to do that because I know you will already learn. I want you to know that, but you will learn it in civil engineering materials. So for this course, all I care about is that you understand just what concrete is and how it generally behaves. So that's all we're really going to care about in this class. What I'm going to do is go over a little bit of stuff related to concrete and steel, some of the pedigree values, the important stuff, and then we're going to get right into it with some example problems. So to start off, let's talk a little bit about concrete. There are some fundamental values that we need to determine, things like its modulus of elasticity, things like its compressive strength. But this one here on the bottom, if you leave this class and don't understand that statement on the bottom, I have failed as a professor when it comes to this class, because there is one fundamental value about typical concrete, and that is concrete is a material that behaves very well in compression and very poorly in tension. And that's why we have reinforced concrete design, is we tend to place reinforcement in all of the regions where a concrete beam is subjected to tension. That's what we do, okay? So if you leave my class and don't understand that, I did something fundamentally wrong. Now, one of the most common ways that we determine concrete properties is to perform a cylinder test. If you all take CE 321, you will do this. If you work on the concrete canoe, you will do this. Am I correct? All right. So we prepare a cylinder. Common size is 6 by 12, although I've seen a lot of outfits moving to the 4 by 8 model for cylinders. Either one I think is really fine for the purposes of what we're talking about here. Cast a cylinder, wait 28 days for it to cure, test it, plot its strength. Okay? So these are some typical stress strain curves that you would get for concrete. And one of the things about concrete is that its behavior is variable. It depends upon the contents of the mix design, how much water content or what have you. And ultimately, you're going to get different behaviors for different types of concrete. And by different types of concrete, I mean concretes with different compressive strengths. One point I will make though is that in the last class in steel design, I mentioned the concept of ductility. Ductility being a material's ability to withstand inelastic deformation. Steel is a material that is highly ductile. Now, all I will say about concrete is that if you compared the behavior of concrete to the behavior of steel, steel is infinitely more ductile than concrete. But if we're just looking at concrete by itself, what we can say is that concrete gets less ductile the stronger it is. So like if we're looking at, let's say, a compressive strength of 3,000 psi or 3 ksi, you can see that this curve sort of trails off of the graph. But for 6 ksi, the curve has a lot less deformation. Does everybody see that? It has more strength, the curve gets taller, but it has less deformation. Okay? So higher strength concretes, yeah, you get more strength, but you get less ductility. That's just a fact of life when it comes to concrete. Everybody good? All right. Now, concrete, by its very nature, is a material that is very highly nonlinear. And what I mean by that is, if you all remember from mechanics of materials, we tend to define, if we can, a linear region of the curve, that elastic region, and then we try and define the inelastic region, the region where we get those permanent deformations beyond yielding. But concrete really doesn't work like that. It's a very nonlinear material. I mean, where's the linear portion on this curve? Well, there really kind of isn't one. The whole thing's kind of nonlinear. But we can, if we want kind of conceptualize something, we can say this kind of tangent slope would be our modulus of elasticity and what have you. And we have models to predict that. Before I pull up this model, there is something I kind of want to point out. I mentioned this to you, I don't know if it was last time or maybe the time before, this whole concept of empirical equations. The idea that there are complex issues that we have to deal with in structural engineering, and we'd like to be able to derive a simple, straightforward plug-and-chug equation. We'd love to do that, but sometimes we just can't, okay? So what we have to do is develop what's called an empirical equation. The idea is we do a bunch of testing, try and curve fit a model, and it works pretty good. Now, reason why I bring this up is because I want to look at this equation, okay? Now, what we're seeing here, this is a prediction for what the modulus of elasticity of concrete looks like. In other words, what this linear slope is right here. I mean, if you all remember from mechanics of materials or structural analysis, that E value is very important if you want to look at strains, if you want to look at deformations. That's really important, okay? This, however, is an empirical relationship, okay? Now, what do I mean by that? You take a compressive strength, a value in PSI, you take the square root of that, and then you get PSI, okay? Those of you who are unit mongers will look at that and go, that doesn't make any sense. Yeah, it doesn't make any sense. It's an empirical relationship, okay? I'm telling you that this curve fit model, you plug in PSI, you will get PSI. So what I have here on this slide are the units that are associated with that model. So for those of you that are familiar with mixed design or what have you, your goal is to try and achieve a target compressive strength. So let's say you get a compressive strength. Let's say it's 4,000 psi. So in this course, we'll refer to compressive strength as F sub C prime, 4,000 psi. And you say, well, okay, well, that's fine. What's the E value? E, you plug it in. Okay, so you plug in your F sub C prime and then your unit weight of your concrete. Now, if you're dealing with normal weight concrete, it's a pretty straightforward calculation. It's pretty plug and chug. Everybody okay with this? Very good. Okay. All right. Now, as I mentioned earlier, concrete is a material that is very, very strong in compression but very, very weak in tension. If you compare compressive strength to tensile strength in concrete, a good rule of thumb is that concrete is about 10 times as strong in compression as it is in tension. That's just the math of it. Now, for tensile strength, we usually what we do is we measure it indirectly. We use a term known as the modulus of rupture. What the modulus of rupture is, to give you kind of an idea, is if I start applying a tensile stress to a piece of concrete, the modulus of rupture is the moment that it starts to crack, okay? That's what the modulus of rupture is. Now, there's a couple ways to do that, and I'm not sure if you do this in Professor Huffman's class, so maybe you can help me out with this. One of them is to actually fabricate a beam and just do a bending test and determine what the stress is when this starts to crack. And this is just sigma equals my over I, what you did in mechanics of deformable bodies to determine that stress. That's one way of doing it. Another way of doing it is the sideways cylinder test. Do you all do this test you do the beam test. Okay, all right. There's two different ways to do it. This is the split cylinder test, where you basically take a cylinder, stick it on its side, and test it that way. And once it fails, you can calculate its modulus of rupture directly from that test data. That's one way of doing it, okay? Another way of determining a modulus of rupture is to actually compute it. You can compute it using the model that's in ACI, which is what we're going to use in this course. So to compute the modulus of rupture, and again, the modulus of rupture is the point at which the beam starts to crack, okay? So that modulus of rupture is calculated as 7.5 times the square root of FC prime times this term lambda. And lambda is just a lookup value. It's a function of what type of concrete you're looking at. Like if you've got typical normal weight concrete, we just say lambda is 1. But if you've got lightweight concrete or sand lightweight concrete, that modulus of rupture is going to be adjusted accordingly. Okay? Does that make sense? Okay. Everybody all right with that? Okay. We're going to use that stuff here in a little bit, but I want to take a little bit of a segue and talk about just reinforcing steel. Okay? Now, the most common one and the one that we're going to employ throughout this entire course is rebar. Okay? I have to predict everybody in this room is familiar with rebar. Am I correct? Okay. So, I mentioned this last time in steel design. For those of you who haven't heard this yet, regardless of what grade of steel you are employing, steel is steel, and it has the same modulus of elasticity. The modulus of elasticity of steel is 29,000 KSI, or 29 million PSI. That will be the same across the board. What changes for steel are its grades. Okay? So there are different types of grades of steel. You can have grade 40 steel, grade 50 steel, grade 60 steel, all under the same umbrella of the ASTM spec for rebar, which if you've had civil engineering materials, you should be familiar with ASTM. Am I correct? All right. So all these different grades do is essentially define the yield stress. So if you're dealing with grade 40 steel, that yield stress would be 40 KSI. If you're dealing with grade 50 steel, 50 KSI. The most common one that we will use is grade 60 steel. So grade 60 steel, the yield stress is 60 KSI, or 60,000 PSI. Everybody okay with that? Now, let's see if you all know this about rebar. If I've got a number 4 rebar, what's its diameter? See if you all know this. What's that? Not a quarter, half inch. Everything up to a number 8, take the diameter, the number of the bar, and divide it by 8, and that's the diameter. So a number 3 bar is 3/8 of an inch in diameter. Number 4, 4/8 of an inch, or 1/2 inch in diameter. That's all the way up to number 8. After number 8, the bar diameters get a little special. This is a table of available bar sizes, and there's also a couple of design guides that I'm going to give you later that have different bar sizes. You might want to star this or put a reference to this in your notes. We will use this quite a bit. If you look, let's see, it's also in the back of your book. I'm almost 100% positive. Let's see. Yeah, if you look at the back of your book and you go to Appendix A, it's right there. In fact, that's where I got this table, was right out of the book. So it's just right here in the back. This is one of those things that you will not need to reproduce on a formula sheet for the exam. You won't need to do that. That's just a waste of time. Okay. Everybody good? All right. Okay. We're not going to use much welded wire fabric or talk about that very much in this course. I just wanted you to be aware of it. Welded wire fabric is something that tends to be used a lot for slab reinforcement and sometimes shear reinforcement in beams. The little bit about the notation, the first 6x12 is about the longitudinal and transverse spacing of the bars, and the second value, like the 16x8, are the areas of the bars. So you can specify the different areas and the different spacings and what have you. But we're not really going to deal much with it. I'm really just more concerned that you understand the mechanics and can go through a basic design, and we're going to get into some of that math today. Right now, I'm just more interested in your, in just that you are aware that it exists. All right. Everybody good? Okay. So I mentioned this to you all earlier that if you take steel design, we actually talk about beams at the very end of the class. In this course, we talk about beams at the very beginning. And we actually spend a lot of time in this class on beams. So I would make sure that you're familiar with things like shear and moment diagrams and things like that. Keep in mind, you have a design guide that I gave you that has all of these moments in there. So what I'm going to do for this discussion is we're going to just take a beam, like a beam in our head, like let's say it's a simply supported beam and a uniformly distributed load. And what I want to do is I want to try and conceptualize what happens to that beam as it begins to fail. Okay? So I take the beam, I put a little bit of load on it, and I keep increasing that load. And I want to look at what happens at that beam, to that beam from the very beginning all the way till failure. And I want to see if we can kind of address those different stages of the beam's behavior throughout. So we're going to talk about behavior of a beam before it cracks, after it cracks, and then what's the ultimate strength of that beam. So the first stage of behavior is what I'm going to call concrete uncracked. In other words, it behaves like any standard typical beam. So, you know, we're talking about a beam that has moderately low levels of load. So the concrete is able to resist those stresses and tension, but not a lot, because there is a point when it's going to fail to resist those tensile stresses, and that's when we reach FR, that modulus of rupture. So, you know, in terms of the concrete being uncracked, you know, we have compressive strains and tensile strains. We have compressive stresses and tensile stresses. Now, this is just something to sort of recap, make sure you all remember this. You all did this in mechanics of deformable bodies. You remember this concept of a transform section, the idea that if you have a beam that's made of two materials, that what you can do is transform one of those materials so that you're dealing with a common medium. So for this class, if you've got a reinforced concrete beam, that's a beam that has concrete and steel in it. What we will ultimately do when we're dealing with cracked sections, we will take the steel and transform it into an effective lump of concrete. And we do that through the use of a modular ratio, the ratio of those two modulus of elasticity. Y'all remember that from deformable? If not, no big deal. We'll review it in here. Now, like I said, this beam that we're talking about, take a beam and just start applying load, it will behave that way, you know, in that uncracked fashion until it cracks. When does a concrete beam crack? It cracks when you reach the modulus of rupture. So you look at this equation, this is little more than sigma equals my over I, and then just solving for the moment. So this applied moment is this cracking moment. We call it the cracking moment. That's when sigma my over I, that sigma equals the rupture strength. So we're just solving for the moment. So we have FR being our modulus of rupture, our gross moment of inertia, which is just the standard moment of inertia of the beam. And then remember what Y is. Remember sigma equals my over I. Y is the distance from the centroid to the extreme fiber. Y'all remember that? Everybody good? Okay. I hope so, because we got an example. All right. So let's take a look at this and digest it. You all have the handout in front of you so you can follow with me. I can take it off the screen when I'm done. But we have a beam, and it is being subjected to a moment of 25 foot kicks. I want to determine what are the bending stresses. So this is just more of a mechanics of materials review. And then I want to determine what is the cracking moment. Okay? So it's a beam that's 12 inches wide, 18 inches tall. Everybody okay with this? All right. Let me pull up my little smartboard thing, and let's see if I can do a little bit of math on the screen. All right. Y'all read that? Everybody good? Okay. All right. So let's deal with part A first. Okay. So what does part A say? Part A says we need to determine what are the bending stresses, right? What are the bending stresses? Well, I mean, let's just go back from the mechanics. The mechanics says that we have a bending stress profile that looks, what? Something like that. And we calculate our stress as what? My over I. Right? Everybody good? Okay. So, a little bit of a review. We need to calculate the moment of inertia. How do we calculate the moment of inertia of a rectangle? What's that? There we go. BH cubed over 12. So you tell me what to write. You got the example in front of you. You tell me. There we go. 12. All right. Everybody read that? Straightforward, right? Now, I will go ahead and plug and chug that for you, and that ends up being .5832 inches to the fourth. How are we feeling? Okay, now somebody else. All right. What we just calculated was that, the I value. Okay. Now what I want to do is I want to look at Y. Okay. Now we go off our bending stress profile. Y is the distance from the centroid to that extreme fiber. So that's Y, right? So somebody tell me, what is Y going to be for this beam? Somebody doesn't have. 9, right? Okay, so how did you do that? Well, Y, we'll use the notation, the consistent notation, Y sub t, is H over 2. Is that a fair statement? All right. So far, so good. Okay. So, we have an applied bending moment. What is our applied bending moment? .25 what? Foot kips. Okay. So, therefore, I can calculate the stress on the bottom of that beam. We'll assume the bottom of the beam is in tension as my over I. Would that be a fair statement? So plug and chug. And we've got that, right? What's the problem? Units, they don't work out, do they? Okay, because this is just a fundamental mechanics problem. So we need to do a little bit of a conversion. Why don't I do this? Okay, and I'll put this in green or something. Why don't off to the side, I multiply this times 12 to convert inches to feet. Now that's a good question. The answer is no, because the only thing I have to convert is this, the feet. It'd be different if I was trying to convert something like this or something like that. And plus, keep in mind, what are we calculating? We're calculating a stress. So a typical unit for that might be KSI or PSI. Okay? So because of that, it would make sense to try and get everything back to inches and not get it back to feet. Now, speaking of that, I think what I'm going to do, just for the sake of discussion, is this would get my units in KSI. If I wanted maybe something a little more manageable, if I wanted it in, say, PSI, I might multiply this whole thing by 1,000 because there are 1,000 pounds per kip. Everybody okay with that? All right, so somebody's got a calculator. Tell me what you get. So about, we'll say, 463. Okay. What do we think? Not too bad, right? Pretty straightforward. Any questions? Keep this. Grab this here. All right. So that's part A. So now what I'm going to do is go into part B. Everybody good with that? Does everybody have what they need on this screen? I'm going to go ahead and go to the next one. All right. So we'll say part B. Okay. So part B for this problem says what I'm going to do is compute the cracking moment. Now, to compute the cracking moment, I'm going to need what? I'm going to need the gross moment of inertia, which I have. I already did that. I've got that centroidal distance, that y sub t, I already have. And I'm going to need a modulus of rupture. Okay? So how do I calculate the modulus of rupture? You tell me. Make sure everybody's paying attention. That's fine. Well, no, I'm more looking for this. All right? Does everybody see that in their notes? Now, if that's the case, what does lambda equal for this problem? 1. And why is that the case? There we go. So lambda equals 1. Okay. Everybody good? Now, therefore, F sub r is 7.5 times 1.0 times the square root of. And this is where you got to start getting used to this right off the bat if the units drive you nuts. It is what it is. We plug in 4,000 psi, and our answer will come out whatever it is in psi. Hence why in that previous problem I wanted to operate in psi, part A. So what is that? 474. 474, we'll say point, I'll go ahead and put the decimal points, 0.3, right? All right. Everybody good? Okay, that's a good question. That was, in part A, that was what is the stress at the bottom of the beam if we apply 25-foot kips. Does that make sense? That's just the resulting stress that you get at the bottom of it. Let me ask a follow-up question to that. Okay, does everybody have something on this screen? Or everything on this screen, does everybody have that? I want somebody in here, based on what we just calculated, can you make a behavioral observation about the answer in Part A? Let me ask it to you this way. The modulus of rupture for this concrete is what? 474 psi? That's what we just calculated? In Part A, we calculated a stress of 463. What did that mean? There you go. This beam hadn't cracked yet. Does that make sense? But it was darn close, wasn't it? Right? 25-foot kips put this beam really close to cracking, right? Let's try and figure out how much moment it would take to crack this beam. Okay? Everybody okay with that? Now, how do we do that? We say that the cracking moment is F sub r Ig over YT, which equals all right. What's the moment of inertia? There we go. And then 9 inches for that, right? Now, this is still a mechanics calculation. Sigma equals my over I. I am solving for a moment, okay? So let's do a little bit of analysis for these units. I'm going to get an answer. What are the units for that answer going to be? If I just plug those numbers into the calculator. There we go. Inch, pounds. Everybody see that? Now, plug that in. Tell me what you get. It's going to be a big number. I have it in front of me, but I'm making you all do a little bit of work. What'd you say? 3 what? 346? Okay. We'll say 350. Because I had 373, and it's probably because I was just carrying the decimals out. So we're not talking about significant numbers. Okay. Now this is inch pounds. If I divide this by 12, what am I going to get? Foot pounds. So divide that by 12. Tell me what you get. We'll just use whatever you calculate, Tony. Yeah. So we'll say 25,612 foot-pounds. Now, what do I need to do to get that into foot kips? So 25 point, we'll say 6.1. Now, let's go back to that behavioral observation. Okay, what did Jared say earlier when we were talking about Part A? We said that the beam hadn't cracked, but it was darn close, right? Okay, look at the moments. On Part A, we had applied a moment of 25 foot kips. What the math just said is that that beam will crack under a moment of 25.6 foot kips, so we were darn close. Make sense? What's that? Yes, sir.
Is it just a coincidence that with your FR value divided by your FT value multiplied by 25 by it get the same answer?
It's not a direct coincidence because everything we're doing right now is linearly proportional anyways. Yes. All right. See how much time we got? Oh, we're doing good. We got plenty of time. Everybody good with this? All right. It's going to get real here in a second. All right. So now we've got, okay, so is everybody good with example 1? Everybody good? All right. Now we've got example 2, and now I made the problem a little more complicated. Now we have a T-beam. We're going to assume that the T-beam is uncracked, and I want to determine what the stresses are on the top and bottom under a moment of 80 foot kicks. Okay? Everybody good? Now, one thing, I did introduce some notation that you all haven't seen yet. You will when we actually start getting into T-beam analysis and design, things like the flange width, the web width, the height of the flange, and what have you. This stuff will make more sense later. Okay? For now, it is what it is. Okay, so let me just ask you this conceptually. What's different about this problem? I mean, this is still sigma equals my over I, right? What's different about this problem? Well, yeah. What is I? Ooh, that one's a little more complicated, isn't it? That one's a little tougher, right? We have to actually compute I. Ooh. Let's talk about that. All right, so let's look at example 2. Actually, let me make that a little bigger. Okay, so example 2, all right, we have a beam something about like this. We need to calculate its moment of inertia, right? Now let me put some dimensions. This top flange is what? Like 60 inches. And this dimension is 5 inches. I can do a little better than that. We'll just say 5. And then this dimension is what? 27? And that's 12. All right. Let's see if you all remember this. We're going to take this, we're going to split it up into simple shapes. We're going to call this upper part shape 1, call this bottom part shape 2, and we'll reference all our centroidal distances from a common datum. Y'all might need to turn your paper sideways because this table's going to get kind of big. Now, I know my mechanics of deformable bodies, folks, we've done this because we did this together last semester. And if you have, I know you've done this before in some of your other classes. But essentially what I'm doing is I'm computing moments of inertia, okay? So we've got shape 1 and shape 2. All right. Now I'm going to start off by listing the areas of these shapes. And here we'll put sums at the bottom. Okay, so let's keep this simple. What is the area of shape number 1? 300, 60 times 5. What is the area of shape number 2? 324. So adding those up, what do you get? There we go. Now, in order to determine a moment of inertia, we need a centroid, okay? Y'all remember centroid, sum of AY over sum of A? Remember that? So I'm going to start off by listing some centroidal distances. Remember, when you compute centroids, you have to express all your distances from a common reference plane or a common datum. So let's keep this simple. Let's start off with shape 2. I think it's easier. How far is it from our common reference line, the datum? How far is it from the datum to the centroid of shape 2? 13.5 inches. There we go. How far is it from the datum to the centroid of shape 1? There we go, 29.5. We don't need to add those up, right? But we do need a centroid, and how do we calculate the centroid? Sum of AY over A. So we need A times Y. So we just take each of these terms and say, what is 300 times 29.5? What is 324 times this? So plug and chug, and you get 8850, 4374. So sum that up, and you get 13,224. Is everybody good? So can anybody tell me what is the centroid of this section? What's the centroid? Plug and chug, and that gives you about 21.19 inches. I'll put a little box over that so that we're all able to reference that. Everybody good? Okay. Okay. Now what we need are moments of inertia. We need moments of inertia of each individual shape. Why? Remember the parallel axis theorem that to determine the moment of inertia of a whole shape, you need the individual moments of inertia plus AD squared. Y'all remember that? I know you did that in mechanics of deformable bodies. I know you did. Well, I know I did it. So, let's keep this simple, okay? For shape number 2, how do we calculate the moment of inertia? Base times height cubed over 12, right? So I'll write that, and I'm going to do it kind of small, so I apologize. But I'm going to say it's 12 times 27 cubed over 12, which is 19,683. Everybody good? Okay. So does everybody see how I wrote this formula? Base times height cubed over 12. So tell me what to write for the upper one. There we go. Exactly. The base is the 60, okay? So it's 60 times 5 cubed over 12. So this ends up being, what is it, 625? Is that what you all get? All right. Everybody good? Now, we're going to need some D distances. And lastly, we're going to have to apply the parallel axis theorem. Okay. Actually, the nice thing about what's coming is that everything else in this whole table is actually very plug and chug. Okay? I'll tell you why. In order to apply the parallel axis theorem, what do we need? We need the I sub naught values, which we have. We need area values, which we have. We need d values, these distances. Now, d is measured as the distance from the centroid of each individual shape to the centroid of the whole thing. Okay? Now, we already have the centroid of each individual shape. We also already have the shape of the whole thing. So in order to determine these, all you have to do is that minus that, that minus that. Just subtract the common value. So what is 29.5 minus that upper value? Or 8.3? I got 8.31. Right? Right? Okay. Oh, wait. That's 29, or it'd be like 29.2, right? If you round it. Oh, okay. All right. So that's this one. The one below, if you keep your signs correct, it'd be negative, and it'd be 7.69. Is everybody okay with that? Does it really matter if I keep track of my signs? No. Why? I'm squaring the terms. It doesn't matter, okay? So how do I calculate what goes here? I take, let's see, this plus that times that squared, right? And I end up getting 0.3. Is everybody else getting that? And then this bottom one, keep track of my colors, I take this plus that times that squared. And I end up getting 854.6. Oh. Are you getting that? Everybody matching that? All right. So add these two up, and I get 60,184.9. So what I'm saying is that for this entire shape, that's the gross moment of inertia. Let's take a moment and let that sink in. How are we feeling about that?
Where did the D come from again?
Okay. All right. Yeah. Okay, that's from the parallel axis theorem. It's defined as the distance from the centroid of each individual shape to the centroid of the whole thing. We've got the centroid of each individual shape, centroid of the whole thing, so it's just that minus that minus that. So if you want, what I could do is put, I'll do it with a little color, I'll say yi minus y bar. Everybody okay with this? Does this answer our question, though? No. The question was asking for the stresses. All this is the moment of inertia, so we're not done, okay? However, what we will do is pick this problem back up next time, which might be Friday, might be Monday, depending on whether or not we are either in Huntington or the storm takes us to Oz. Everybody good?
I vote Oz.
You vote Oz.
You vote Georgia.
All right. That's all I got. I will see you all next time.